Chapter 5, Energy and Thermochemistry. What is energy? The universe is made of matter and energy. And matter is all of the stuff in the universe, all of the things that have mass. And energy is what makes those things move. So if the universe only contained matter, then nothing in the universe would be moving. So the fact that we see not only things, we see planets and stars, but we also see them moving, that the movement of those objects relative to each other is a manifestation of energy. So energy can't be created or destroyed, but it can be transformed. It changes forms. Einstein discovered that matter and energy are interconvertible. E equals mc squared. Energy equals mass times the speed of light squared. So here's an example of matter being converted into energy. This is one of the biggest implications of Einstein's equation, is that contained within even a very, very small amount of matter, there's a great amount of energy. So m, the mass in this equation, the number could be very small. We could be talking about this item right here, for example, what this man is holding in his hand, could create a bomb with this kind of devastation. And the reason is because the small amount of mass is multiplied by this number squared, and c is the speed of light. And the speed of light is a very big number. And that very big number squared means that very big number times itself. So even a very small amount of matter has a huge amount of energy. Here's an example of energy being converted into matter. So if a laser light with enough energy is shined in a device like this, the energy kind of bounces around inside of the device, and the photons can create electrons and positrons, which are a form of matter. So energy and matter are the two parts of our universe, but they can be converted into each other. There are lots of forms of energy. So here is a list with some forms of energy. This is not an exhaustive list. There are far more than this. Gravitational energy affects all mass, and on Earth, the center of mass on Earth is where everything is being pulled toward the center. So this gravitational force field pulls everything toward the center of the Earth. Electrical energy affects charged mass, and so the particles that have positive and negative charges, positive charges repel each other, positive and negative charges attract each other, and this is one way of representing that attraction, those forces. Magnetic energy is very similar, except the two pieces are connected. The north and south pole of a magnet, the positive and negative charge are connected. Elastic energy affects deformable materials like springs. Radiant energy like light, microwaves, radio waves. Thermal energy is a measure of kinetic energy. Nuclear energy is the energy that's contained within atomic nuclei. Sound energy, the energy contained within vibrating particles in the air. Chemical energy, energy found within chemical bonds between atoms. So thermal energy is the energy associated with the movement of particles. So when something is hot, the particles are moving faster, and when something is cold, the particles are moving slower. So the thermal energy is a measurement of the movement of the particles. Chemical energy is a measurement of the energy that's contained within the bonds of a chemical. For example, this chemical here, glucose, these lines are the bonds that hold the atoms together, and there's energy contained within those bonds. So I could have a sample of glucose that I pull out of the refrigerator, and it has low thermal energy. And if I leave it out on the table and it warms up a little bit, then it has higher thermal energy. But the chemical energy of glucose was not changed in that example. The chemical energy of glucose was the same when it was cold or when it was warmed up, but the thermal energy changed as it warmed up. It gained more thermal energy. So temperature is a measurement of a substance's thermal energy. So we've looked at this before, the comparison of different temperature scales. There's a Fahrenheit scale, Celsius scale, and Kelvin scale. And the difference is between Fahrenheit and the others, they have a different size of the degree. The degree itself is a different size. And they all have a different 0 point. So 0 for water, for Fahrenheit is 32 below freezing point of water. 0 for Celsius is the freezing point of water. And 0 for Kelvin is absolute 0, the coldest point in the universe. There are chemical reactions that involve heat exchange, where we can have a chemical reaction that warms up, or chemical reactions that cool down, that get colder. So when a chemical reaction heats up, that's called exothermic. The heat is leaving the solution, and that heat can enter your hand, for example. You can feel it getting hot. An endothermic reaction is one that starts to cool down, where the heat is entering the reaction. And so if your hand was holding this flask, this beaker, the heat would be drawn out of your hand into the reaction, and your hand would feel cold. The internal energy is the sum of all potential and kinetic energy of all particles in the system. So we'll talk more about potential and kinetic energy in a little bit, but essentially the internal energy of a system is all of the energy that's contained within that system. It's everything. So one way of representing that energy is with an E, and energy, that E is equal to heat plus work, Q plus W. So heat and work we'll talk about here in a minute, and kinetic and thermal, or kinetic and potential energy we'll talk about here in a minute. But the internal energy of a system is the sum of all of the energy. It's all the energy in the system. So heat is this energy equals heat plus work. So heat is part of that energy. And heat is the chaotic transfer of energy from one system to another. So when something heats up, the particles start to move in all directions equally and kind of randomly. Heat, we can see that in these arrows here, that as something starts to heat up, the particles kind of move in all directions equally and randomly. Work, on the other hand, is the transfer of energy from one system to another in a uniform motion. So for work to be done, all of the particles have to be going the same way. So when I heat something up, all of the particles move in every direction. But if I were to get all of the particles to move in the same direction all at the same time, they could bump into something, and they could cause that thing, maybe it's a windmill or something, and they could cause it to spin and impart some energy. So in order for work to be done, there needs to be a uniform motion. All of the particles need to be going in the same direction. Here's an example of work being done. So as the water flows through the flume and it hits the water wheel, then all of the particles in this water are going the same direction, because they're being fed by gravity, presumably, and the water is moving downhill. And so all the particles are going in the same direction. And as they hit this water wheel, they can start to spin the water wheel around and do some kind of work. So if if the particles are all moving in a uniform direction, in the same direction, then they can do work. You can imagine if the water particles were going in every direction and not in just one direction, maybe equally in this direction and this direction, then the wheel wouldn't turn. Well, that's an example of heat. In heat, the particles are not moving in one direction, they're moving in all directions. So I can't capture the motion because any motion up is canceled by an exact amount of motion in the downward direction. So here's another example of work being done where I have chemical energy inside of a battery, and if I connect the positive and negative terminal to a load like a light bulb or something, then the electrons can travel around this circuit. So the electrons are repelled from the negative side, and they leave the negative side and travel through the circuit, and when this switch is closed, the electrons can move this way. As they travel through the light, they heat up the filament, and as that filament heats up, it causes the filament to produce light and heat. So a light bulb lights up and gets hot. That's because the electrons are moving around inside the filament. And so the electron goes from here and goes through the switch and goes through the filament and heats it up and then goes right back to the battery, to the positive terminal of the battery. So the work is the example of the electron moving around the circuit. And heat, when the light bulb heats up, you can feel that heat being generated in every direction. Everywhere around the light bulb gets hot. Kinetic energy is the energy of motion that is being transferred. So kinetic energy is when something is moving. Thermal energy is kinetic energy that's associated with the energy of the particles themselves. And sometimes we call that temperature when we're measuring the average of the kinetic energy in a sample. So when a ball is moving on a pool table, for example, that ball has kinetic energy, and if it hits another ball, then it can transfer the energy to that other ball, and that's called work, because that ball is moving in a uniform direction. And after it transfers its energy, then the first ball might stop, and the second ball would start to move as it takes that energy. One definition of energy is the capacity to do work. Another way to think about energy is as motion. So when things are moving, that's what we think of as energy. So they can move in different ways. They can move in a chaotic fashion where all the particles move kind of randomly in all directions equally, and we call that kind of movement heat. Or the particles can all move in a uniform direction where they all go the same direction, and we call that kind of motion work. So energy can take two different forms. It can take the form of kinetic energy, which is energy due to motion where the particles themselves are moving, or potential energy, which is energy due to position. So to think about one example of kinetic energy, kinetic being that things are moving, thermal energy where the particles in an ice cube are kind of stuck in place and they're moving very slowly, we would call that one example of low thermal energy. And if I took that ice cube and heated it up and it melted, and then I boiled it and those water particles turned to gas and they were moving very quickly and the steam was very hot, then that water would have very high thermal energy and the particles would be moving very quickly. So the energy that's associated with the motion of those particles, either in ice, they're not moving, so low thermal energy, or in steam where they're moving very fast, high thermal energy, that energy is a manifestation of the motion of the particles. Potential energy is energy that's due to position. So, for example, we looked at the chemical bonds in a molecule of glucose that hold the atoms together. So a chemical bond between a carbon atom, between two carbon atoms, there's energy within that bond, kind of like a spring that holds two balls together. So we can kind of think of chemical bonds as springs. Just like there's energy inside of a spring, there's energy inside of a bond. So potential energy is energy that's due to motion. It's energy stored in an object due to, it's energy due to position. Potential energy is energy stored in an object due to its position. So this rock is not moving. If you saw this rock and it was perched very precariously like this on the edge, you probably wouldn't want to get underneath it because it might fall, but at the moment it's not moving. So if it's not moving, we can't say that it has kinetic energy, because kinetic energy is when things are moving. So this rock doesn't have kinetic energy, but like I said, you would not want to stand underneath it. And the reason you don't want to stand underneath it is because it has some kind of energy, because you would be scared that it could crush you. So if that rock were on the ground, then you wouldn't be scared of it. Or if you were up here, you wouldn't be very scared of that rock. But if you're down here underneath it, you would be pretty scared of it. So this rock has energy based on its location due to its position. So if it's up here and you're down here, then the energy that it has is due to the gravitational field. This rock could go lower because it's being pulled toward the center of the Earth. And so if you happen to be underneath it on its way toward the center of the Earth, then you will get crushed because it has a lot of mass. The water behind this dam is not moving, so it doesn't have any kinetic energy. But if this dam were to break suddenly and all of this water came pouring out, then we would say that there must have been some kind of energy within that water all along, and the dam was stopping that energy. Excuse me. So potential energy is the energy that a system has due to its position. The energy that are between that are within chemical bonds between atoms, that's potential energy. Kinetic energy, on the other hand, is the energy of motion. So when the water is falling, it has kinetic energy. But when the water is just sitting here, it has potential energy. If the dam breaks and the water falls, then the potential energy is converted into kinetic energy, and then it starts to move. So when we're talking about energy, we have to talk about energy being transferred from one system to another system, or from the system to the surroundings. So when we're talking about the system, we define that as the material or the process within which we are studying. So the system is the thing that we're trying to focus on, and we want to know how the energy is changing within that particular arrangement. The surroundings are everything else with which that system is in direct contact, or with which that system can exchange energy. So if I'm performing a chemical reaction in a flask, it's on a table. So the chemicals are actually inside the solution. Right, so I've got these chemicals that are inside the liquid. So the liquid, let's say that it's water. So in this solution, the green ones and the red ones are going to react. So the system is green plus red. Makes green red or something. So if we imagine that this is the reaction that's happening, a green one and a red one are going to run into each other, and they're going to make this green-red one. So this is the system. The system is the chemical reaction itself. It's this whole process. System. The surroundings is everything else. So the surroundings are the air, the water, the beaker, the table. It's all of the things that are surrounding the system, the particles themselves having this chemical reaction. So when we're trying to study the energy that's associated with this chemical reaction, we have to think about the fact that that system is surrounded by a lot of stuff. And so whatever energy exchange is happening within this chemical reaction, it's also being exchanged with the surroundings, with all of this other stuff that's around it. So, for example, if this were getting hot, right, so plus heat, this reaction makes a green-red one and it makes heat. So it's getting hot. So as it gets hot, the water gets hot. And as that water gets hot, the flask gets hot. And as the flask gets hot, the table gets hot. And as the flask gets hot, the air gets hot. And so there's all of these exchanges of energy happening. The energy that came from the system is now exchanged with the water and the air and the beaker and the table, and all of these different pieces of the surroundings are now involved in this energy transfer. The first law of thermodynamics. Thermodynamics is the study of energy and its interconversions. So the example we were just talking about. The first law of thermodynamics is the conservation of energy, which is that the total amount of energy in the universe is constant. So you can never design a system that will continue to produce energy without some source of energy. So for a system to move, it needs to have energy of some kind, and so it can't produce more energy than the fuel that is making it move in the first place. So you can't get out more than you put in. That's one way of restating the first law. You can't get out more than you put in. So if you push a ball down on a spring and you load some energy into this spring by pushing it down, by compressing it, then when you release it, it's going to push the ball up. The spring will release and it will push the ball up, and the height that the ball travels against the gravity is equal to the energy with which you pushed the ball down into the spring in the first place. So that amount of energy is equal. So the conservation of energy requires that the sum of energy changes in the system and the surroundings must be zero. So again, if you push the ball down on the spring and you let go and the ball shoots up in the air, the ball can't go higher. It can't have more energy than you put into the system in the first place. In fact, that exchange has to be equal to zero. The amount of energy you put in is exactly equal to the amount of energy that comes out. So we saw that energy, the internal energy, E, is equal to Q plus W. Q is heat and W is work. So energy equals heat plus work. Another way to represent the internal energy is with a U. So delta E and U are two symbols for the same thing, which is the internal energy. and the internal energy is all the kinetic energy and all the potential energy within a system. So when we're talking about the change in energy, we're talking about energy being exchanged between the system and the surroundings. And when that happens, when a chemical reaction occurs and it gets hot and it's heating up its surroundings and it's exchanging energy, there are two ways that it can exchange energy. One way is heat, which is the example we're talking about, things getting hot as the reaction gets hot. Another way is through work. So systems can exchange energy through heat and through work. So delta E equals heat plus work, Q plus W.